Welcome everybody to this presentation. I'm Joerg Hoffmann, in case you're wondering, and let me get right into it. What we're talking about here are situations where you need to take complex decisions in dynamic environments and ideally in real time. For example, if you're controlling a drone, or you're trying to rescue some sort of disaster, or you're trying to control some sort of factory. Now, more and more people are telling us that we should be doing all of those using neural networks. And in particular, some of those people are present right here at ICAPS and at PRL. Now, the question I'm asking, that we are asking, is if we are supposed to just execute that policy, that neural network in our disaster that's surrounding us, how are we supposed to get trust that it's actually going to do the right thing? Now, of course, we're not the first people to ask that question. There's lots and lots of approaches that can help with this. And lots of work has already been done in the ICAPS and large AI community. One keyword is missing here that's really quite an obvious answer to the question how to gain trust. Well, testing. It's a scalable method. It's very useful. Everybody knows that. Now, despite that, everybody knows that this can be useful. I found a little work in the AI community on testing in the context of neural networks to take images as input and where you have no model of the environment, but I'm not aware of anything at ICAPS. And so our ambition here is to close that gap. Now, you might ask, is this actually planning? Well, depending how narrow you want to be in your notion of planning, you might not want to have testing methods at ICAPS, I don't know. But even if that is the case for you, I can assure you that some of this is just planning in the usual meaning of the word. Does this belong to PRL? Well, I don't know. You tell me at the end of the talk. I am actually thinking of establishing a new workshop along the lines of trusted AI planning. So happy to discuss this later. But now let's discuss what we actually did here. If you're wondering what planning formalism we address, the answer is basically whatever you want it to be. The only assumption we are making is that it makes sense to learn a policy and that you can define a value function for the policy. Now, you might think in some cases defining a value function really makes no sense and isn't commonly done. For example, if all you worry about is whether or not your plan, your policy reaches the goal. Now, also in that setting, you can define what we call a qualitative value function that just measures the degree to which you reach the goal. We're going to be using V star as usual for the value of the optimal policy, generalizing over planning frameworks that minimize or maximize. I also have this notation on the slides. However, I'm not going to explain any of the actual technical statements using this notation, so I'm going to skip this over here. Now, let's define what a bug is in planning. Well, it is simply a state in which the policy performs suboptimally, where, in other words, the optimality gap compared to V star is greater than 0. It is very easy to find lots of intuitive examples where you have this sort of thing. Observe that if a policy is bug-free, this is just another way of saying it is optimal. So many of the things we're spelling out here just correspond to kind of viewing common planning concepts and notions through the new lens of action policy testing. Now, you might have thought that an easier and more intuitive definition of bug is, well, the policy returns a suboptimal action. However, for that definition, it would actually not hold that the absence of bugs implies optimality, because you actually need to coordinate those action choices across different states. So this definition that we have here is sort of the strongest, most general one. We also introduce a definition of fuzzing bug, where you compare a state as prime to another state S, and then you say that S prime is a fuzzing bug relative to S if the optimality gap at S prime is larger than that at S. So basically in this situation, if you don't know the exact optimality gap at S prime, but you do know that it's larger than about at S, then you know that S prime is a bug. So this kind of comparison arises naturally in the context of fuzzing. And we can make some very simple observations about it. So first, if S prime is a fuzzing bug relative to some state, then it's a bug. So this is a special case of bug, if you will. Is that special case very restricting? Well, not at all. As soon as if you have a single, in every state whose optimality gap is non-minimal, is a fuzzing bug relative to some other state, namely a state that has a minimal optimality gap across the state space. Now, given those observations, you might wonder why introduce this definition at all. It basically seems to be another word for bug. Well, first, like I said, it's natural if you have a fuzzing algorithm. Second, The second observation here, number 2, doesn't hold under restrictions on the reachability of S prime from some state S. So there might be some state S somewhere in the state space compared to which I'm a fuzzing bug, but actually reaching S prime from S might be quite difficult and not possible under a particular restriction to a fuzzing algorithm. So in practice, this definition gets a little bit meaningful. And also one might wonder whether this definition might help in bug confirmation. I've already hinted to that, in fact. Bug confirmation is what we call a problem of deciding, given the state S, whether or not that state is a bug. If you're trying to use the fuzzing bug definition, you would also have another state. You would have 2 states, S prime and S, and would try to decide whether S prime is a bug, given its comparison to S. Now, obviously, this decision problem is just another word for optimal planning. I mean, it subsumes optimal planning, right? You have to find the optimal solution for S in order to decide whether or not the policy you're considering has a bug at S. So I told you it is planning, didn't I? Now we have to do optimal planning in order to solve the problem. So we approximate. Here is one of our approximations. I'm not going to explain how it works. I'm just going to say that it all boils down to evaluating the value of the policy pi at S and trying to find a better policy. So this might be kind of disappointing. We were thinking about how to use optimistic and pessimistic approximations and all that. You can plug in all the things that planning people know to do, and it all boils down to just, well, try if you can do better. Now, so we turned our attention to fuzzing bugs, and again, we wrote quite some complex theory about how you can identify fuzzing bugs in practice using optimistic and pessimistic approximations. And after we did all that, we again proved that it all boils down to evaluating the policy and trying to find a better one. Okay, so lots of theory work for not much practical implication. Well, actually, there's a practical implication, right? It tells us what we can and what we cannot do, but actually it tells us what we cannot do. But what can we do then? Well, first, the good news is that in many practically relevant or relevant seeming cases, you actually have a V-star oracle. Namely, for example, if the question you're asking is whether the policy reaches the goal, and if the state space you're considering in classical planning, for example, happens to be invertible, and so you know that all states are indeed solvable, then you have a V-star oracle for the qualitative value function. It's 1 everywhere. Another possible scenario is that where at runtime conditions you have very little time, and so you need the policy to be able to react directly to a new situation. However, at testing time offline, before you bring the policy into execution, you might have enough time to actually use an off-the-shelf symbolic planner as your oracle. In the general case, if none of those conditions applies, you're just gonna have to use the plan quality improvement algorithms, and luckily there's also quite some planning literature on those, and you can plug them right in. Okay, that's it. Outlook. Well, I've told you a lot of things, but I haven't actually done anything, right? So it's up to us all to actually do what I just outlined. We are proposing a framework here. It remains to actually implement the framework and see whether it does anything useful. We are about to embark on this. In fact, we are already doing this. And I very much hope that other people will feel inspired to join us in this endeavor. The things that can be done are many, and I'm not going to even try to enumerate them here. And this is the end of my presentation. Thank you very much.